Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, we shall continue next chapter 3.5, the specialization method. Okay, the specialization method is used when statement in hypothesis contains the quantifier for all or for each. Okay, at the end of this section, you'll be able to prove the statements involving the universal quantifiers, like for all, for every, for each, for any, in the forward process. And you'll be able to identify the certain property for all objects and something that happens, and to choose object by using the choose method. Okay, yes. Alright, in this session, we also use choose method in specialization method. Say regarding choose object, so we have to use choose method. Okay, specialization involve quantifiers for all. Okay, in the standard form of forward process A, for all objects with a certain property such that something happens. Okay, for example, this is simple one. If you can think of this, how to identify object and certain property and something happens. Object here, object is Ford. Alright, certain property made in 2000. Then something happened, get good gas mileage. That means something happens. This is the result. Okay. Alright, in this section, you must learn to identify the three components. Alright, here again, in choose method also, we identify three components. There are a certain object, certain property, and something happen. Right here, and then after you identify these three things, right, three components, you should look at one particular object. You look for one particular object here. To look for a particular object, you use a choose method. This particular object arises in backward process, right? And then after you choose the object, right, you should verify this particular object, this one where this part where the specialization comes in. Okay, verify the particular object have the certain property in the for all statement, right? And then lastly conclude that something happened for this particular object, right? So here to conclude, you should write a new statement in a forward process. Okay, let's go to more understand about specialization. So let's look at this first example. If R and S are convex sets, then R intersection S is a convex set. So here it's about convex set. So the definition of convex set is this, right? You can refer to the book, right? Definition of convex set. And from this statement, all right, we know that R and S are convex set. This is hypothesis. And R intersection S is a convex set. This one is a conclusion. So it's clearly that we want to show that R intersection S is a convex set. So to write the next step, okay, should be B1. B1, because B statement is this, right, the conclusion. So of course we have a question, isn't it? The key question is that R intersection S is convex set. So what is that convex set? So here we get the answer of key question. So B1. B1 is the definition of convex set. Okay, take this definition, put it here. So for all, using the word for all elements X, Y in A. Set A change to R intersection S. R intersection S is also a set. So replace A to R intersection S, and for all T with, okay, you copy everything, is just the set change to R intersection S. Okay. So observe that at a backward process, B1 is considered backward. Okay. Backward process, there is a quantifier for all. Okay, quantifier for all at backward process. So by using choose method, so you should write a new statement in after you choose That is a A1 statement, new statement in for process A1. You choose an element AB other than XY. Okay, choose an element other than XY. Here I use the variable AB in R and S, and also choose other than T, which is K. Okay, I use K with K from 0 to 1. Then to show this, you want to show this one. You want to show that KA change everything that you have chose here. AB, AX change to A, Y change to B, and then T change to K. Okay, stop here. Okay, stop. You've done this. You clear what you want to find. You want to show is clear. Then to proceed the proving of this statement, you must read the hypothesis. Okay, read the hypothesis. R and S are convex sets. So there are two hypotheses here. R convex set, S convex set. Okay, so start with forward process A2. Write the definition of a convex set. So here a set A changed to R. So and then X and W, since at B1 statement already use X and Y. So I would like to change to other variable, right? VW in R, and for all Z. Okay, so this one also change because we have used a T in B1, so change to Z, Z from 0 to 1, and the last statement. So here at a forward process, okay, forward process for all, for all exists in a forward process. So here we use specialization method. Okay, you want to what? To specialize what? To specializing A2 to the object that we have chosen. Okay, here you have chose AB, right? And then you should specialize. This part is actually to verify the object, the chosen object. Verify the chosen object. Okay, so V equals to A, right? W equals to B. You want to replace that V to A, and you specialize V to A, and then you specialize W to B, you specialize Z to K. Okay. Okay, this one A2 is for R is a convex set. How about S is a convex set? So again, using A4. A4. Okay, I forgot to tell you about A3. A3 is the answer of this one. Okay, and then this is for R. I said R. And then S is a convex set. Again, we use definition of convex set. Okay, this statement get from A, the second case about S is a convex set. So for all RS here, other variable, using other variable RS in S, and for all U, okay, everything you write similar as in definition of convex set. So now again for all in a forward process, so using specialization method, so you want to verify the object, specializing A4 to R equals to A, S equals to B. Here A and B is the object that you have chosen, and U equals to K, right? After that, the answer of this, okay, KA plus 1 minus KB in S. So now you combine A3 and A5, combine these two statements to get A6. Therefore, KA plus 1 minus KB in both sets, okay, R and S. So this one proof and the proof, okay, equivalent to B2. So to write the condensed proof, all right, we can start with the conclusion to show that R in S, R intersection S is a convex set. So first use a choose method. That's why this word come. Let A be in R intersection S, and let K with K from 0 to 1. So from hypothesis says that R is convex. So in particular, so you use word in particular shows you are verifying the object. In particular, you stress the object. That means you use specialization. this part. Word let is for choose, in particular is for specialization. In particular, one has that KA plus and this one in R, and then similarly in S, right? Thus, it follows that this statement, right, this expression in both sets R intersection S. And so R intersection S is convex. And N, your statement is small. You should put small box to show the end of proof. And the proof is completed. Okay, next example. All right, this proposition regarding convex function. Okay, so we want to use a definition of convex function. So it is clear that all right, A is this statement, okay, and B is this statement. After then, right, this proposition is to show that the function SF is convex. So S is the real number. So then write the definition of convex function for all real numbers s greater equals to 0 and for all elements x, y, t with this one blah blah blah. Okay, you follow the definition of convex function. Okay, all right, choose because B1 has for all. This one for all universal quantifier at backward process. So using choose. So when you use choose, you should start your new statement forward process. That is A1. An element, choose an element other than x, y, and t. So here I use x prime, y prime, and t prime. Okay, and then to show this, right? That okay, for all this one come from where? Come from this one. Okay, this part choose. Okay, this one is finished, right? You stop here, and then you should start with the forward process. Take from hypothesis. F is a convex function of one variable. So for F is a convex function, you should follow definition, and then this is where A2. Okay, A2 for all, okay, you copy everything in definition for all x, y, t, okay. So for all in a forward process, so therefore we should specializing A2 to x equals to x prime, y equals to y prime, and t equals to t prime. And the objects that we have chosen, okay. So A3, this is the result of this one, okay. And then multiplying A3 with real number s. So real number s, real number you can multiply with a function. When you multiply real number with a function, so this is true. So the statement is true. Why true? Because s is a positive number. So because s is a positive number, so when you multiply with a function, so the sign of inequality does not change. Yeah. So that one proof your analysis. Complete your analysis of proof. Then after that, write a condensed proof. We start with the conclusion to show that the function SF is convex. This condensed proof is just an example. Okay, you can write your own style. This is my style. Okay, to show that the function SF is convex. So first of all, you should let is for choose. Okay, and then from the hypothesis, f is a convex function. In particular, here shows a specialization. In particular, okay, this statement multiplying both sides with real numbers. Okay, as it follows that this one, okay, true since s greater than 0. So that's the function sf is convex, and then end with the small box to show that the proving is completed. Right, next proposition, we have subset and upper bound. So there are involve two definitions. One's for subset, another one is for upper bound. Right. This statement from after if and before then all is a hypothesis. And statement from after then is a conclusion. So the conclusion part, U is an upper bound for R. We have a definition of upper bound, and then this gave a statement B1. All right, statement B1 for all elements M in R, M less equals to U. See, follow this definition, right? So here for all in a backward process, so suggest a choose method. You want to choose other than M, which is an element R in R. And then you want to show that this M M change to R less equals to U. We want to show that U is an upper bound. Okay, R less equals to U. You want to show this. Okay, done. You stop and then you should back to forward process. So to back to forward process, you should look at hypothesis. Here, hypothesis says that R is a subset of a set S. Right? R is a subset of set S. So you should write definition of R is a subset of S. Here, definition for all elements. X in R, X in S. So you should know the definition of a subset. We have done this in section 3, chapter 3.4, choose method. Okay, so you can see this for all. The word, the quantifier for all is at forward process A2. So this one suggests of specialization method. So verify, you should verify. This specialization method is to verify object in A1. So R in R, right? R in R. In A1, R in R. So has a certain property in R. Okay. So you specializing A2, this one, specializing this to R. Right? So R in S. Okay. So therefore you get R in S. Then after that, okay, again, R is a subset of S, and U, the other one. There are two hypotheses here. Okay, one is for R is a subset of set S. So that is first case. R is a subset. This is first hypothesis. And U is an upper bound for S. This is second hypothesis. Okay. So you done the first hypothesis. R is a subset of S. So second one, another one is U is an upper bound for S. So recall the definition of upper bound for all elements S in S less equals to U. Right? This is the definition of upper bound. Then you see that for all in a forward process here, for all in a forward process, okay. So suggest to use specialization method. So you verify object in A1. Here A1 is R, isn't it? Choose object R. So you specializing A4 to R. Now R less equals to U. Therefore, you have shown that U is an upper bound for S. Is that clear? So this is equivalent to B2. Okay. So for condensed proof, okay, you can start from conclusion to show that. So to start from conclusion, you should use the word to show. Okay. To show that U is an upper bound for R. So let R in R. So by hypothesis R subset S and R in S. Furthermore, by hypothesis U is an upper bound for S. Thus, every element S in S less equals to U. So in particular, R in S, so R less equals to U. Okay, so done. All right, conclusion for specialization method. So when to use it? When A has a quantifiers for all, for each, for every, for any. For every object in a standard form. See that A is in a forward process. In a standard form, for every object with a certain property, something happens. So what to assume? You assume A. What to conclude? You want to conclude B. Okay, how to do it? Work forward by specializing A to one particular object having the certain property. Okay, so I hope this one is clear, right? So next one, I would like to proceed to nested quantifiers. If the statement has a nested quantifier like this one, for example, prove that for every real numbers x greater than 2, there is a real number y less than 0 such that x equals to 2y over 1 plus y. Prove that for every. So this one, prove that, that means you want to show that proof for every, here for every is at backward process, right? Prove that this is backward. The word after proof that, okay, this is not in a standard form. A if A implies B, isn't it? This statement is not in standard form if A implies B. So, but you have to understand that after the word proof that, okay, of course, this is backward process. Okay, so such that is the input. Such that this one is input. So such that is the hypothesis. So for every real numbers x greater than 2, there is a real number y less than 0. So can you see the word for every at the backward process? So here you should use what technique should use? Choose. Yes, very good. So you should choose. You should use choose. Sorry, because universal quantifier at backward process. So what to choose? You should choose a real number x. Every real number x greater than 2. A real number x. Okay. There is a real number y in right. Choose a real number x. Okay, supposed to choose other than x. There is a real number y less than 0. There is. So here there is. Okay, choose method, of course, after you use choose, okay, choose, you must start with a forward, and your new statement must forward process with backward process. One step, okay? So here there is, okay, there is, this one is existential quantifier at backward process. Remember? So when the quantifier there is at backward process, so what method that you should use? Should use construction method, isn't it? So what to construct? What to construct? Which one? Which object to construct? The desired y, isn't it? This is the object. You want to construct the desired. There is a real number y. Okay, that means you want to construct y. Okay, using construction. So let's look at my my working. All right. Okay, done. So A2. So you finish the you are clear what you want to prove. So A2, we start with forward process. Here you get from hypothesis, right? X equals to y over 1 plus y, and then x equals to okay, you simplify this one. You simplify until you get y. Here the in the previous slide I use x prime, x prime, so I should write x prime here. Sorry about that. This one I should write x prime because I choose this x prime. This also x prime, x prime, x prime. Okay. All right. So x prime equals to this one, and then you simplify, you multiply x prime with 1 plus y, and then you get the, okay, change, okay, rearrange xy, and then to y, okay, to y minus xy equals to x. Then because you want to get y, isn't it? You want to construct y, okay? So y is equals to x prime over 2 minus x prime. So this one is less than 0. Why is it less? It's true less than 0 because x greater than 2. Okay, it's given that x greater than x greater than 2. Alright, so and then okay, done the analysis of proof. Okay, to write the condensed proof, let a real number x greater than 2, and to construct y. Okay, from hypothesis, therefore y is equals to x over 2 minus x, since x greater than 2, so y less than 0. For every okay x. Alright, never mind. Okay, that's a real number x prime. I just put prime. We should put prime. Okay, so done. Next, that has a nested quantifier. Prove that the function, okay, is bounded above. There is and there is a real number y such that for all real number x, fx less equals to y. So analysis of proof. This one is bounded above. Okay, B statement. This one should be bounded above and proof. This is B statement. B statement conclusion proof. So B statement, alright, is bounded above. So you should get the definition of bounded. There is a real number y such that for all real numbers x, and this one, this statement. Okay, negative x squared plus 2x less equals to y. Okay, this one is a function fx. Okay, less equals to y. There is a real number. Okay, there is in a backward process. So this suggests using construction, right? Using construction. So what to construct? You want to construct the desired y. So here there's no formula to construct y. So let's do try and error. Here I try y equals to 1 first. Okay, y equals to 1. When I try y equals to 1, so and then I rewrite the statement for all okay, here for all real numbers x. So and then you get negative x squared plus 2x less equals to 1. Less equals to 1. So here for all at backward process. So this suggests using choose method. Right? So you should choose method. So what to choose? You choose a real number x prime. Then you want to show that this one. Then, alright. Then this one, okay, you just rearrange. Rearrange the inequality you get before. So after that, factorize before. Okay, you will get okay. So a2 x prime minus 1 square. This is square x prime minus 1 square, right? So this equivalent to before. So this one is done. You finish this. Okay, clear about this. Okay, you clear this. You clear about this one. This one you clear. Okay. All right. You choose a real number x prime. And then what to show? This is what you want to show. Okay, you want to show. And then B statement, B4 is actually alright, to get it's the same to B2. B4 is the same to B3. Sorry, B4 is the same to B3. This one is the same. But to make it more clear, what we want to find, actually what we want to prove is just that this number 1 just rearrange inside. Then you will get okay, you combine everything, then you get the statement before greater equal to 0. That means the statement here, the expression here is a positive number. Okay, positive number. So we done this. Then after that, you should proceed with the forward process. So proceed with forward process. You should look at hypothesis. Right here, hypothesis. Where is hypothesis here? The hypothesis, okay, prove that the function is this is bounded above. There is a real number. Okay, the hypothesis is this one lah. Yeah. X prime minus 1 square greater equal to 0. This is what you want to show lah. Okay. So this is equivalent to before. Equivalent to before. Equivalent to before. Actually, they are the same. They are the same. X prime minus 1 square greater equal to 0. Okay, so for condensed proof, okay, to show that this one is bounded above the function, so by definition there is a real number y, such that for all real number x, okay, this statement, to construct the desired y by try and error leads to y equals to 1. So you let x prime equals to r, x prime real number, okay, and then you plug in x, change x to x prime, that's equals to 1. Then you rearrange this inequality, you get next statement of inequality, then you factorize it, you get the final answer, which is x prime minus 1 square is greater equals to 0. We want to show that so greater than 0. Okay. Right, so then that give you two examples for nested quantifier. Because sometimes we have to use more than one technique, two or three techniques. It depends on the quantifier in the statement. Okay, so for that I end the class. Okay, this section with tasbih kifarah and surah wal as. So assalamualaikum warahmatullahi wabarakatuh.